Hi there, I'm Surajit and you are welcome to our channel. In last video lecture, we have talked about spherical polar coordinate system. In this video, uh, we'll discuss about cylindrical coordinate system. So let's start. So as we have noticed in cylindrical coordinate system, in spherical polar coordinate system, to represent a point, we need three variables r, phi, z, and also we have noticed in rectangular coordinate system, to represent a point, we need three variables x, y, z. Similarly, in cylindrical coordinate system, if we want to represent a point, we need also three variables. So what are these three variables? So for that, let me draw a cylinder. Let's say this is a cylinder. Let's say this is a cylinder whose axis is parallel to the z-axis. This is the z-axis. And center is lies at the origin of the coordinate system. And this is the y-axis. And let's say this is x-axis. X-axis, y-axis, z-axis. And its center the cylinder lies at the origin of this coordinate system, and its axis is parallel to the z-axis. Now consider a point inside the cylinder. Let's say this is a point, let's say P point, and it has rectangular coordinates, say x, y, and z. X, y, and z. Now if this point we want to represent according to cylindrical coordinate system, then how many variables is required? So in cylindrical coordinate system, first we define the perpendicular distance of this point from its axis of the cylinder. So for that, what we have to do, we have to draw a perpendicular on the z-axis. Okay, so this is the perpendicular distance of this point from the axis of the cylinder, and that we define, we represented by rho. Second, this point must be lie in some plane. Let's say this is the plane. This is the plane. So we have to see what is the angle between this plane and the positive x-axis. This angle. So this angle is represented by phi. And third variable that is that required to represent this point. So that is what is the height of this point, perpendicular distance from this point from the xy plane. What is the perpendicular distance of this point from the xy plane? That is this distance, and usually we represent this distance by z. By z. So now to represent this point in cylindrical coordinate system, so we need three variables. And what are these three variables? First is perpendicular distance from the axis, that we represent by rho. Second is this point must be lies in some plane, so we have to see what is the angle between this plane and positive x-axis there, that is represented by phi. And third is what is the perpendicular distance of this point from the xy plane, that we represented by z. So if this if we want to represent this point by cylindrical coordinate system, that we can represent by this three variable rho, phi, and z. Okay? Rho, phi, and z. Now either we represent this point by rectangular coordinate system or we represent by cylindrical coordinate system. Both the cases will represent the same point with respect to the same origin. So again, there must be some relations between x, y, z and rho, phi, z. as we have noticed in 2D polar coordinate system and spherical polar coordinate system. Same way, here also we can write this xyz in terms of rho phi z. So for that, what we have to do, so let me first join this point with the origin. Yeah, this is the position vector of P. This is the position vector of P. So when we represent this point by xyz, so this xyz represent the projection of this OP vector on the x-axis, on the y-axis, and on the z-axis. So in order to write the value of xyz in terms of rho phi z, what we have to do, we have to take projection of this r vector, OP vector, on the x-axis, on the y-axis, and on the z-axis. So here you can see already the perpendicular distance of this point from the xy plane is z, and then if we draw a perpendicular line on the axis of the cylinder, so this will be the projection on the z-axis of this OP vector, and it is already, we have written here z, so it must remain z, so it will be z. Now if we take projection of this vector on the xy plane, so this will be the projection, and that is also, we already defined this perpendicular distance. The perpendicular distance of the point from the axis of the cylinder is represented by rho, so this distance will be rho. Okay, rho. So now we have to take projection of this rho on the x-axis and on the y-axis. So now you can see this rho is making an angle, makes an angle phi with the positive x-axis. So projection of this rho on the x-axis will be rho cos phi. So for that, what we have to do, we have to draw a perpendicular line from this point on the x-axis. So this is the perpendicular line, and also we have to draw a perpendicular line on the y-axis. Okay. So now these two length, this length and this length, they will give us actually the projection of rho on the x-axis and on the y-axis. And from the figure we can write that if this distance is rho, then rho makes an angle phi with the positive x-axis. So projection of rho on the x-axis will be rho cos phi, and projection of rho on the y-axis will be rho sin phi, rho sin phi. So once we know the value of once we know the projection length of the OP vector on the x-axis, y-axis, z-axis, so now we can write the value of x, y, z in terms of cos phi. So here we can write from the figure. Let's write here from the figure. We can write x equals to rho cos phi, y equals to rho sin phi, and z in this case will remain z. Z. Okay. So now what we have to do, once we know the value of x, y, z in terms of rho phi z, then what we can do, we can write the position vector of P with respect to the origin. So the position vector of point P, position vector of point P with respect to origin O is RP vector. First, let me write in terms of rectangular coordinate system. So what we'll write? We'll write xi cap, yj cap, and zk cap. Then we can replace this xyz in terms of rho phi. So what we'll get here, if we replace this x by this rho, So x will be replaced by rho cos phi. So rho cos phi I cap plus rho sin phi j cap, and z in this case both in cylindrical coordinate and rectangular coordinate system remain same. So z into k cap. So this is the position vector of point P in terms of cylindrical coordinate system. In terms of cylindrical coordinate system. So as we have defined in spherical polar coordinate system, unit vector associated with each variable. Similarly, here also we can define the unit vector associated with each variable. For that, what we have to notice here, that the position vector is function of how many variables. So in this case, we can see in cylindrical coordinate system, the position vector is function of rho, function of phi, and function of z. So again, it's a function of 3 variables. So we can define 3 unit vector associated with each variable. So in next page right here, the unit vector associated with the rho, usually we represent is represented by rho cap. So rho cap, and how we'll define this rho cap? For that, let me write again this position vector rp. Rp equals to what we have written just in last page, rho cos phi I cap, rho sin phi j cap, and zk cap. So now to define this rho cap, what we have to do? First, we have to take the partial differentiation of this position vector with respect to rho, and then we have to divide by its magnitude. Okay. So this is our position vector rp. So first we have to take a partial differentiation of this rp with respect to rho. That's mean we have to differentiate this rp with respect to rho, keeping phi and z fixed. So when you do that, what we'll get cos phi I cap plus sin phi j cap, and then we have to divide by its magnitude. What will be the magnitude? Magnitude will be cos square phi plus sin square phi. So this will give you denominator. Take a look at denominator. It's under root cos square phi plus sin square phi. Cos square phi plus sin square phi is 1. So denominator give you 1. So from there we can write rho cap is equals to cos phi I cap plus sin phi j cap. So this is the unit vector associated with rho. So it's a unit vector. Magnitude of this unit vector will be 1, and the directions of this unit vector give us the direction along which we can increase the value of rho in cylindrical coordinate system, keeping phi and z fixed. Second, then write the unit vector associated with phi. So the unit vector associated with phi usually we represent it by phi cap. And how we'll define this phi cap? So for that, again we have to take the partial differentiation of position vector rp with respect to phi, and then we have to divide by its magnitude. Okay. When you do that, what we'll get here? We'll get minus row sin phi I cap plus row cos phi j cap, and then we have to divide by its magnitude. So it will be rho square into sin square phi plus rho square into cos square phi. So if we take common from the denominator rho square, then what we'll get sin square phi plus cos square phi, which will give you 1. So we'll get under root of rho square, and if we take outside of the under root, we'll get rho. And in numerator also both the term have rho, so from numerator to denominator we can cancel out this rho, and finally what we'll get phi cap is equals to minus sin phi I cap plus cos phi j cap. So this is our unit vector associated with the variable phi cap in cylindrical coordinate system. So again, this is a unit vector, so magnitude will be 1, and the directions of this unit vector give us the direction along which we can increase the value of phi in cylindrical coordinate system. And now the unit vector associated with z. So the unit vector associated with z, usually we represented it by z cap, so z cap is equals to, same way you can define this, take position vector and then differentiate with respect to z, partially differentiate with respect to z, and then divide by its magnitude. So in this case you will get simply k cap. So in this case z cap will write k cap parallel to its axis. Okay. So these are the unit vector, and that's what this z cap give us you along, this is give you the directions along which you can increase the value of length of this cylinder. We can increase the length of the cylinder along this direction. Now once we know the mathematical expression of rho cap, phi cap, z cap, we can visualize this point, this rho cap, phi cap, z cap on the cylinder. This is necessary because again, when we're going to solve the problem, this maybe this mathematical expression will we have to use, but at the same time, so if we have this visualization which directions this rho cap represent and which direction phi cap represent and which direction z cap represent, then it will be easy to understand the problem. So that's why let me just draw a cylinder here. This is the cylinder, and this is the axis of this cylinder. In this case, it's a z-axis, and let's say this is y-axis and this is x-axis. Okay, so now if we want to represent a phi cap or rho cap and z cap at any point on the cylinder, how we can represent? For that, let me just consider one point. Let's say at this point. And so first, what we have to define rho cap. Rho cap. So for that, what we can do, let me just consider a point here. So for this point, let's say this is the P point, and if we connect with the origin, this will be our RP vector. So what will be the coordinate of this point according to cylindrical coordinate system? Let's say radius of this cylinder is rho. So perpendicular distance from the axis rho, and then this r vector is parallel to the positive x-axis, so phi in this case will be 0, and it is lies on the xy plane, so z will be also 0. Okay, so at this point, if we want to calculate the value of r cap, z cap, phi cap, we know the mathematical expression. Okay, you can see rho cap is function of phi, phi cap is also function of phi, and z cap will be always parallel to the k cap, or to be positive k cap. So at this point, if we want to find out rho cap, so what we have to do, we have to put value of phi is 0 in this equation. If you put phi is equals to 0, what will get? Rho cap is equal to I cap, and phi cap will give you plus j cap. Okay, so at this position, our rho cap will be in this direction, plus I cap, and then phi cap will be positive j cap, so it will be in this direction, and z cap is plus k cap, so z cap will be in this direction. This is rho cap direction, this is phi cap direction, and this is z cap direction. Okay, now consider this point. For this point, what will be the cylindrical coordinate system, cylindrical coordinate of this point? So again, this is on the surface of the cylinder, so perpendicular distance from the axis will be rho. Now this point, if we connect with the origin, so this r vector will make an angle phi with the positive x-axis. So this rho will make an angle phi with the positive x-axis. So phi will be in this case 90 degree, pi by 2. And then again, this point is on the xz plane, so z will be 0. So now if we want to find out the value of r cap, rho cap, phi cap, so what we have to do, we have to put the value of phi is equals to pi by 2 in this equation, in this equation and here. When I put the value of phi by 2, what we'll get here, we'll get rho cap will be plus j cap, phi cap will be minus I cap, and z cap will remain plus k cap. So in this case, rho will be in this direction. This will be the directions of rho cap. Phi cap will be minus I cap. So in this figure, you can see if this is y, this is z, then x will be out of the phase. So at this point, phi cap will be into the phase. So circle with a cross, that will give you directions of phi cap. And then if any vector is directed into the phase, then we'll represent circle with a cross. If it is out of the phase, then we represent circle with a dot. Circle with a cross into the phase, circle with a dot out of the phase. Okay, so at this point, rho cap will be positive y-axis j cap, and phi cap will be minus I cap, so into the phase, and z cap will be plus k cap direction, so in this direction. Z cap will be in this direction. So from these 2 points, what we can generalize here, that rho cap will be always actually radial outward. You can see here, rho cap, when you take a point on the positive x-axis, it will plus I cap direction. When you take a point on y-axis, its direction is along plus j cap. So rho cap will be always actually radially outward. Rho cap will be always radially outward. So if we consider a point here, then or here, what will be the directions of rho cap? So if this is the center, then rho cap will be in this direction, radial outward first, radial outward. And then phi cap, for phi cap, what we have to do, phi cap, we have to draw a circle about the z-axis. About the z-axis, consider rho as a radius of the radius. We have to draw a circle, and then if we draw a tangent on this circle in anti-clockwise direction, in anti-clockwise direction, that will give you the directions of phi cap. So in this case, this will be the direction of, if we draw tangent at this point on this circle in anti-clockwise direction, so this will give the directions of phi cap. So this is rho cap, this is phi cap, and z will be always parallel to the positive z axis, or you can say plus k cap, so it will be upward direction. Okay, so at any point of the cylinder, if you want to represent the rho cap, what we have to remember, that rho cap will be always radially outward. Rho cap will be always radially outward from its axis. And then phi cap, for phi cap, what we have to do, if this is the cylinder, and we want to represent any point, let's say this point, then what we have to do, this is the cylinder, then we have to draw a circle which will pass through this point like this about z axis. And then if we draw a tangent on this circle in anti-clockwise direction at this point, that will give you the directions of phi cap, and z cap will be always parallel to the positive z axis in this direction. Okay, good. So now we know the directions of r cap, phi cap, z cap. So next, what we have to define, we have to define, we know the directions of rho cap, phi cap, and z cap. And now what we have to define, elementary length in cylindrical coordinate system. Elementary length vector in cylindrical coordinate system. So the concept of elementary length will remain same. It doesn't matter if either you are considering rectangular coordinate system, or you are considering spherical polar coordinate system, or you are dealing with a cylindrical coordinate system. In each cases, the concept of elementary length will be remain same. This means, as we have considered in the rectangular coordinate system, let's say this is x-axis, y-axis, z-axis, and we have a large length, and for some calculations we need to break down this length into a small part, and the smallest possible length is will define as elementary length. Same way in cylindrical coordinate system also, when we talk about elementary length, that's mean we are considering, let's say, 2 point in the cylindrical coordinate system, and this is a large length, and if I want to divide it, break down this large length into small length, so what will be the smallest possible length in cylindrical coordinate system, and how we can represent this in cylindrical coordinate system. So we know how to write this elementary length in rectangular coordinate system. So now we want to write this same elementary length in terms of cylindrical coordinate system. And where we're going to use that type of questions, that type of concept, and again we'll see, we'll get some, we can have this type of problem, that where electric field will be given in cylindrical coordinate system in terms of rho phi z, and if the examiner asks what is the potential difference between between 2 point, that time also first we have to consider elementary length in cylindrical coordinate system, and then we have to take dot product with electric field, and then we have to integrate over the length, and that will give us the potential difference between these 2 points. Okay, so for that, what we have to do, we can just write this elementary length separately, like elementary length along rho cap, elementary length along phi cap, elementary length along z cap, and then we can write them together, and that will give us elementary length vector. So for that, let me draw a cylinder first. Let me draw actually 2 coaxial cylinder. So this is inner cylinder. This is inner cylinder, and this axis is parallel to the z axis. And also, and a radius of this cylinder, let's say rho. Rho. And also, let me draw another coaxial cylinder. Another coaxial cylinder, and radius of this cylinder is say, let's say rho plus d rho. And what is d rho here? Let's say we have a cylinder of very large radius, capital R, where capital R is very, very large. So when you're going to limit of this rho, what will write? 0 to capital R. So now, since rho is varying from 0 to capital R, so we can increase the value of rho step by step, and the smallest possible increment of rho is represented by d rho. So at d rho is very, very small length. D rho will be very, very small length. So now the question says, if you are, let's say, on the inner surface, inner cylinder, at any point on the inner cylinder, and you want to go outer cylinder along the directions of rho cap, along the directions of rho cap. So everywhere, how long you have to travel, how much length you have to travel? Everywhere you have to travel this distance. So this distance will be d rho, this distance will also be d rho, this distance will also be d rho, this distance will also be d rho. So any if you are on the inner surface, and from inner surface if you want to go outer surface along the directions of rho cap, everywhere you have to travel d rho distance. So that's why this elementary length along rho is written along rho cap direction is written d rho cap. It will represent as dl rho is equals to, right, d rho cap. D rho cap, that will be the elemental length along rho cap. Now to define the elemental length along phi cap, let me draw another cylinder here. Yeah. So let's say this is the axis of this cylinder. Z axis. Now consider a point. Let's say radius of this cylinder is rho, and consider a point here. And also define it, let's say this is y axis and this is z axis. Okay. So now if we draw a plane which will passes through this point, this is the plane. Now this plane makes angle phi with the positive x-axis. This is the plane. On this plane we have considered a point P here, and this plane make an angle phi with the positive x-axis, and radius of this cylinder is rho. Okay. So now, keeping the radius of the cylinder fixed, if I want to represent the value of phi by small amount, say d phi, what will going to happen? All point that is lies on this plane, they will also shifted by an angle d phi. And which direction they will shift? So if we increase the phi, this is the phi. Now what I am going to do here, I am going to increase the value of phi by a small angle d phi. Then all the point that is lies on this red plane, it will shift it to this white plane. It will shift on the white plane, on this plane. On this plane. So what is the value of this angle? This angle is d phi. The angle between these two planes is d phi. This angle is d phi. This angle is d phi. So now if I ask you, what will be this distance? You see, initially this point was here. Now when we increase the value of phi by an angle d phi, this point will shift here. This point will shift here. So what will be the distance between these 2 points? This length. So for that, we can see the perpendicular distance of this point from the axis is rho. The angle between these two planes is d phi. So this distance will be rho d phi. Rho d phi. Now already we know the directions of phi cap. We have already know here directions of phi cap. Phi cap will be anywhere on this circle. If we do a tangent in anti-clockwise direction, that will give you the directions of phi cap. So from this idea, we can say that this elementary length will be generated along the directions of phi cap. Directions of phi cap. So that's why that this length is written as elementary length along phi cap, d phi cap. So we represent it as a dl phi. So dl phi be rho d phi phi cap. Rho d phi phi cap. And finally, we have to define elemental length along z cap. So for that, what we can do, we can just draw two coaxial cylinder. Both the cylinder have same radius rho, but the length, let's say first cylinder have length z, and second cylinder have a length z plus dz. They both are coaxial. The radius are also same rho, but the second cylinder has length d plus dz. This is the second cylinder. And this cylinder has length z plus dz. And what is dz here? Dz is the smallest possible increment of z. So now again, same questions. If you ask yourself that if we want to, let's say you are on the top surface of the first cylinder here. Now if you want to go from here to here along the directions of z cap, I mean top surface from z length cylinder to z plus dz length along the directions of z cap, how much distance you have to travel? Everywhere you have to travel dz. Which direction? Plus z cap direction. So that's why in elemental length along z is written dz z cap, dz z cap. So now we know the elemental length component along rho, along phi, along z. So we can write the general elemental length in cylindrical coordinate system. dl length is equals to d rho cap phi along the elemental length along phi. So elemental length along phi, that is rho d phi phi cap, and then dz z cap. Okay, dz z cap. This will be the elementary length vector in cylindrical coordinate system. Cylindrical coordinate system, where d rho is the elemental length component along rho d phi is the elemental length along phi, and dz is the elemental length along z, along the length of the cylinder. Okay. So once we know the elementary length, then we can define elementary area and elementary volume. Elementary area and volume. But when we talk about cylindrical surface has two kind of surface actually. Let's say, let me draw a cylinder here. So this is a cylinder. So you can see this top surface and bottom surface. They have flat nature. That's why it is called flat surface. However, this surface is actually called curved surface. So top surface, bottom surface is called flat surface, and this surface is called actually curved surface. So here we have to define elementary area on the both surface, top and bottom, that is flat surface, and on the curved surface, top surface and curved surface. So for that, I'm considering a small part of cylinder, which length, let's say elementary length dz, and uh, so this is a part of a cylinder, part of a cylinder, whose length is dz. So this length is dz. Okay, and so this is the axis of the cylinder. Z-axis is the axis of the cylinder, and radius of the cylinder, let's say rho. Radius of the cylinder is rho. And also I am drawing another cylinder, coaxial cylinder, whose radius is r plus dr. So radius is r plus dr. And its axis also parallel to the z-axis. Okay, parallel to the z-axis. Good. Now what we have to do, we have to define an elementary area and elementary volume. So for that, what I am considering here, let me consider a point here. Consider a point here. So it has perpendicular distance from the axis is rho, because that the inner cylinder has radius rho, so this distance will be rho. And let me just draw a plane that will be passes through this point. Let's say this is the plane. Okay, and this plane makes an angle with the positive x-axis, let's say phi. Okay, phi. So now what I am doing here, keeping the phi fixed and value of dz fixed, if I increase the value of rho at this point by d rho, then what will going to happen, this point will shift from white surface to red surface along the directions of rho cap in this direction. This will shift here, and also at this point will shift bottom surface, this point will shift here. Okay, so what will be this length from here to here or here to here? This will be d rho, and this will be d rho. Now again come back to this position, top surface at this position and the bottom surface at this position. Now what I am doing here, I am increase the value, keeping the value of rho fixed. What I am doing, I am increasing the value of phi by a small angle d phi, a small angle d phi. Then what will happen, this point will shift from here to here, and this point will also shift here to here. And if we draw a plane that will passes through these 2 points, then we can say all the point before increase the value of phi, all the point, those are lies on the white plane. When after increase the value of phi by an angle d phi, all these plane will shift to the red plane. Will shift to the red plane. So what will be this length now? This length or this length? So inner cylinder have radius rho, and this angle is d phi. This angle is also d phi. So if this angle is d phi, then what will be this length? This length or this length? This length will be rho d phi. This length will be rho d phi. So now you can see, if we draw a parallel line of this line at this point, this will be like this, and then if we connect these two, so this will form a elementary area on the bottom surface. Same way, if we draw a parallel line of this line from this point, and parallel line of this line at this point, this will also give you a elementary area on the top surface of the cylinder. Top surface of the cylinder. So these are two elementary surface that will be generated on the top surface and bottom surface of the cylinder. So that's mean the flat surface. So now the question is, what will be the area of this portion? So we'll write elementary area ds, and since it is flat surface, we'll write flat on the flat surface. So what will be the value of this ds? One side is d rho, another side is rho d phi. So it will be rho d rho d phi. Rho d rho d phi. Now cylinder is closed surface. It will enclose some volume. So definitely it is a closed surface. So for direction, what we have to do? We have to draw a outward normal. Outward normal. So if we draw an outward normal on this surface, it will be upward direction, and on this surface it will be downward direction. So if it is on the top surface, then we will write plus z cap. If it is bottom surface, then we'll write minus z cap. So we can write plus minus j cap. For top surface, it will be plus z cap, and for bottom surface, it will be minus z cap. Yeah, good. So this is the elementary area on curved surface. On the flat surface. Now also we can define elementary area on the curved surface also. What will be this area? That we can also see from this figure actually. You see, what will be this area of this portion? Area of this portion. This length is dz. This length is dz. And from here to here, this length is rho d phi. Rho d phi. Then what will be this length? And this area. And this is the area, elementary area on the curved surface. And what will be the area of this portion? It will be, one side is rho d phi, another side is dz. So it will be rho d phi dz. So the elementary area on the curved surface, ds on the curved surface, will be rho d phi dz. Rho d phi dz. Now if we draw a normal to this surface, which directions it will go? It will go radially outward. So it will be rho cap direction. Okay. So this is the elementary area on the curved surface of a cylinder. Curved surface of a cylinder. Now what you have to do? Elementary volume. So for that, what I am doing, I'm just connecting this point, which is this point, and this point with this point. Okay. And let me just remove this line. A little bit more. Yeah. So now you can see we have a cuboid portion whose top or bottom surface is like this, flat. Yeah, this portion, and height of this portion is dz. So we know the base area. Base area is rho d phi, and we know the height dz. So what will be the volume of this cuboid? This cuboid, see, this is the cuboid. So what will be the volume of this cuboid? So we have to just multiply length with this cross section area, rho d phi into dz. That will be the elementary volume in cylindrical coordinate system. So elementary volume in cylindrical coordinate system, dv equals to, what will write, rho d phi and dz. Okay, rho d phi and dz. And what is the concept of elementary volume? It will remain same. Let's mean if we put this type of small volume side by side, up and down, then we'll give a volume of the big cylinder. So this is the smallest possible volume in cylindrical coordinate system. Yeah. So now we know the elementary area, elementary volume, elementary length. What we have to define, one more thing here, that's limit of these variables. Limit of the rho, phi and z. What will be the limit of rho, phi and z? So what will be the limit of rho, phi, z? So if we consider that whole universe in cylindrical, then in this case, usually we define this, the limit of this rho will be 0 to infinite. But most of the time we will deal with a finite cylinder. So for that, what we'll write, if the radius of the cylinder is capital R, then we write the limit of the rho will be 0 to capital R. Limit of the phi. So phi, you can see here, if this plane make an angle phi with the positive x-axis. So if we rotate this plane about the z-axis by n 2 pi, so again it will come to the positive x-axis, come back to the positive x-axis. So after 2 pi, every time it will repeat the same path. So the limit of the phi will be 0 to 2 pi. And the limit of the z, and again, if this want to represent the whole universe by this cylindrical coordinate system, then we'll define it minus infinity to plus infinity. But if it is a finite cylinder and the length of the cylinder is, say, let's say capital L, and the coordinate system, origin of the coordinate is at the center of the cylinder, for that case we'll take the limit of z is minus L by 2 to plus L by 2. And if you set the coordinate, origin of the coordinate at the in point of the cylinder, then we take value of the z is from 0 to 10. Okay, so these are the limit of different variables in the z coordinate, in the cylindrical coordinate system. And yeah, so this is enough related to the coordinate system. So in next video we'll talk about different kind of different mathematical concept that is required to understand the electrostatic phenomena or magnetostatic phenomena or dynamics phenomena. So we'll talk about in next class. Anyway, thank you for watching and we'll see you in the next video.